Hello APC Mechanics students in Unit 1 Kinematics, Class 18, Projectile Motion Part 4. In today's video, we're gonna solve some exercises related to projectile motion, in particular parts 1, 2, and 3. Then exercise 1, two projectiles are launched with the same initial speed from the same location. Both have the same initial speed. Then speed is not a factor. One at a 30 degrees angle and the other at a 60 degrees angle. Then both angles are complementary. They sum up to 90. With the horizontal, they land at the same height at which they were launched. Then this is a symmetric projectile. If air resistance is negligible, how do the projectiles' respective maximum heights and times in the air compare with each other? Then h30 is the maximum height of the 30 degrees angle, similarly h60. And the same for T30 and T60. We know that the time of flight and the maximum height for a symmetric projectile or a projectile are affected by two things: the launching angle and the initial speed. The initial speed is the same, so they are only affected by the launch angle in this case. As theta increases, then the time of flight and height increases, which means T60 is greater than T30 and H60 is greater than H30, and in this case the correct answer would be E. Exercise 2. A spring-loaded gun can fire a projectile to a height h if it's fired straight up. If the same gun is pointed at an angle of 45 degrees from the vertical, what maximum height can now be reached by the projectile? Then we're trying to compare the heights. So this is the initial height, and let me say that the maximum new height is given by h2. We're trying to check how does the launching angle affect the height. We know that the maximum height is given by v0 square sine square theta divided by 2g. Initially, the projectile is fired straight up, which means that theta would be given by 90 degrees. Then the initial height given by h, small h, is given by v0 square sine 90 degrees to the power of 2, and that would be 1, divided by 2g, which is given by v0 square over 2g, which is the same expression for a free fall motion with an initial launch upward. Now we need to check the new maximum height in relation with the previous height. Then h2 in this case would be given by what? v0 square. Remember that theta is the angle with the horizontal, not with the vertical, but since the angle with the vertical is 45 degrees, which means that the angle with the horizontal is also 45 degrees, because 90 can be split equally into 45s, then that would be sine 45 to the power of 2 divided by 2g. And that would be equal to v0 square multiplied by half divided by 2g. We can factor out half. That would be half multiplied by v0 square divided by 2g. And this is basically the initial height. So that would be half multiplied by h. And in this case, the correct answer is given by C. Now exercise 3, a plane is moving horizontally through the sky with a speed v. A package is dropped from the plane and travels a horizontal distance x from the point of release to where it lands on a target. If air resistance is negligible, the height from which the package is released is, then basically we're interested in the height, which is the vertical position, and it's given by y0 plus v0 sine theta t minus half g square, given the fact that the positive direction would be chosen to be up and the origin is the point of launch. Now the package is released from the aeroplane. Then in this case, the velocity of the package would have the same velocity of the aeroplane, which is a horizontal velocity. And in this case, the launch angle theta would be 0. Then Vy0 would be 0 in this case, which means V0 sine theta would be 0, because if theta is 0, then this is gonna be 0. So that would be 0. And if the origin coincides with the point of launch, so that would be 0, then the vertical position is given by minus half gt square. The final vertical position is at height h, but h is being measured opposite to the positive direction, then that would be minus h is equal to minus half gt square. then minus and minus cancel, then the height is given by half half gt square. However, if you look at the choices, we need to replace time in relation with the horizontal position, and we're gonna refer to this equation. X is given by x0, v0 cosine theta t. Now the initial position coincides with the origin, and theta is 0, which means that this is 1. Then x would be given by the initial speed, which is v, multiplied by t. Then t can be expressed as x divided by v. Now replacing this here, and we're gonna have half g multiplied by x over v to the power of 2, and in this case the correct answer would be D. Now exercise 4, the toy raft shown in the top view above is sliding due east on a frictionless ice at a constant speed. Then this toy raft, initially it's sliding toward the east with an initial velocity v0 on frictionless ice, so there is no friction. When a fan blows on its sail, producing a constant acceleration a directed to the north, which of the following could indicate the path of the raft while the fan is blowing? Now this problem is completely similar to a projectile, because notice that if we have an object launched with initial velocity v0 along the horizontal, we know that in the case of a projectile, acceleration is always downward, and in this case the trajectory is gonna be a parabola like that. So this is the trajectory. Now this is similar to that. Why? Because the acceleration is in this case up, not down. So we're gonna have that the acceleration is up, and we have initial velocity to the right. Then in this case the trajectory would be something like that, which is an inverted trajectory of a parabola, of a projectile, and the correct choice in this case would be A. Now exercise 5, an object is launched with the velocity v0 shown. The horizontal, basically we're talking about a projectile launched with an initial velocity v0. The horizontal and vertical components vx and vy respectively of the initial velocity are shown. Okay, fine. If air resistance is negligible, which of the following best shows ax and ay when the object reaches the highest point in the trajectory? Independent of any point of the trajectory, both components ax and ay would be the same. We know that there is no acceleration along the x-axis, then it's either A or B. And we know that due to the downward acceleration due to gravity, sorry, let me repeat, because gravity is always pointing down, the acceleration would be downward, then in this case the correct choice would be B. Now exercise 6, a target T, capital T, lies flat on the ground 3 meters from the side of a building that is 10 meters tall. As shown above, a student rolls a ball off the horizontal roof of the building in the direction of the target. Air resistance is negligible. The horizontal speed with which the ball must leave the roof, if it is to strike the target, is most nearly. Then we're searching for the horizontal speed. Now here, because the ball will be launched from the roof of the building, then let's suppose that this is the point of launch, and because this is horizontal, then the projectile will have a horizontal velocity given by that. Then theta, the launch angle, would be 0, and the horizontal speed would appear in the equation of the horizontal position given by x is x0 plus v0 cosine theta t. Now theta in this case, which is the launch angle, this is 0, then cosine theta would be 1, and let's suppose this is the point of launch which coincides with the origin. The positive direction is chosen to be up in order to make use of the equations of motion we have determined previously. X in this case would be given by v0t, and we're searching for the value of v0. Then v0 is given by x divided by t. We know that the horizontal position traveled by the projectile from the side of the building to the point T is given by 3. Now what about the time? The time can be determined by referring to the equation of the vertical position, which is given by y is y0 plus v0 sine theta multiplied by t minus half gt square. Theta is 0, which means sine theta is 0, and this is 0. Another reason is that because the vertical velocity is 0, the initial position coincides with the origin, which is the launching point, and in this case y would be given by minus half gt square. Now we need to find the value of time. The vertical position is given by negative 10 meters because the positive direction is up, so minus 10, which is given by minus half. Now let's choose g to be 10 in order to simplify with that. T t square, then 10 cancels with 10, negative cancels with the negative, then t would be given by t square is 2, then t would be given by radical 2 seconds, and that would be 3 over radical 2 meters per second, and in this case the correct answer is C. Now exercise 7, a small sphere is launched horizontally with a speed v0 toward a target a horizontal distance d away. The sphere lands on the target that is at height h below the height from which the sphere was launched. Then let's do a sketch. Then let's assume that this is the point of launch with a horizontal speed v0 at a height h above the landing point. That would be the landing point at a distance d. If the sphere was launched again but with a speed 2v0, then we're gonna change the speed from v0 into 2v0. How high above the target would the sphere have to be launched horizontally to hit the same target? Still a horizontal distance d away. The horizontal distance d didn't change, it would remain d. However, now we need to find the new height. Then let's determine the expression of the height, and the height is given by the vertical position given by y. Now in order to make use of the previous equations, we need to set the origin to be the launching point, which is this, and the vertical position to be upward. Then in this case this is y0 plus v0 sine theta t minus half gt square, and because this is being launched horizontally, then theta is 0, which makes this 0. The initial position coincides with the origin, which is the point of launch. Now what about the final vertical position at this landing point? Measured opposite to the positive y direction, that would be minus capital H, which is minus half gt square. Then minus cancels with minus, that would be capital H is given by half gt square. We need to find the new capital H. Now this depends on time. We need to convert time to position and velocity, and this can be done by making use of the horizontal position equation. X is given by x0 plus v0 cosine theta multiplied by t, that would be 1 and that would be 0. Then x is given by v0 multiplied by t, and t is given by x divided by v0. X is the horizontal position, which is given by capital T divided by v0. Now the expression of h in terms of d and v0 is given by half g multiplied by d divided by v0 to the power of 2. Now because we have double the speed, we can apply the factor of change. Half didn't change, g stays the same, d stays the same, so this can be replaced by 1 multiplied by 1. The speed is doubled, and that would be to the power of 2, which is 1 over 4. Then in this case the correct answer is E. Exercise 8. Pairs of students stand in 2 rows separated by 4 meters and face each other. Each pair of students has a large ball. The students pass the balls from their chest to their partner's chest as shown. A video camera is used to film this interaction. When viewing the video, the students know that the highest point and the trajectories of all the balls are nearly the same height above the ground. Which of the following claims is supported by this evidence? Then upon shooting the video, they've noticed that both balls thrown from each other, they follow the same trajectory. We know that the trajectory of a projectile is being affected by 2 things, by the launch speed and the launch angle. Then in order for basically we're assuming that they're being launched from the same horizontal location. Then in order for both projectiles to have the same trajectory, they need to have the same launch speed and the same angle. Then which of the following claims is supported by this evidence? Part A, the students threw the ball to their partners with nearly the same speed. No, this is not enough. We should have speed and angle. The students threw the ball to their partner at nearly the same angle to the horizontal. No, that's not enough. We need also the same speed. Now the time the ball is in air is nearly the same for each ball. Let me keep this as a choice. I will explain why. It is impossible for the balls to not go to the same height because the distance between each pair of students is the same. No, it's not about the distance between the pair of students. Each ball must have the same mass. No, we know that the equations of motions are free of mass. They don't depend on the inertia. Now, why the time the ball is in the air is nearly the same for each ball? We're talking about the time of flight, because indeed the time of flight, it happens that it depends on two variables given by the initial speed and the launch angle. If the launch speed and the launch angle is the same, which means that the time of flight is the same. So by choosing C, we're saying that basically that they're launching the ball with the same speed and with the same angle. Now exercise 9, which is an exit ticket for today's video. Two rocks are thrown simultaneously from a height h above the ground as shown. Rock A has a mass m and is thrown horizontally with a speed v0. Rock B has a mass 2m and is thrown with a speed v0 at an angle theta above the horizontal. Which of the following statements is true? Now let me do a small recap, that if an object is left freely to fall, the impact speed would be given by a radical 2gh. This is case 1. Now case 2, if the object is launched downward with a speed v0, the impact speed in this case would be given by radical 2gh plus v0 square. Now believe me or no, whether we launch this object with the velocity v0 but with a different direction, like this or like that or like that, the impact speed would be also given by v is radical 2gh plus v0 square. You can think about it as symmetry. If the object is thrown at a different direction, it will go up, then it will fall down with the same slice of height, having a velocity inverted, and it will have the same impact speed. This is one way to think about it. Another way this can be investigated using energy in unit 3. Now let me do a recap about what I have said so far. Now, if an object is left to fall freely, the impact speed would be radical 2gh. And if an object is dropped with the velocity v0, independent of the direction of this velocity, whether it's completely downward or at an angle or completely upward, the impact speed upon hitting the ground would be given by radical 2gh plus v0 square. But basically here what's happening is that rock A is being launched with the velocity v0, and rock B will be launched with the velocity v0. Both are being launched with the same velocity, the same speed, but different velocities in a sense that the angle is different, which means that they will hit the ground with the same speed, independent of the value of the masses, whether rock B is 2m and rock A has a mass m. Then C would be the correct choice. Rock A and B hit the ground with the same speed. Then that's it for me in this video, guys. See you soon in a new one.